So a list of top 19 countries by 2017 emissions. All right, level of global total and percentages. I forget where I got, oh, I got this from Wikipedia. It's one of my, well, it's everybody's go-to, but I usually like to go to like the CIA World Factbook or, you know, something like that to get data. But I try to get as accurate data as possible. But what we need to do here is get this data into a calculator because we know we're going to have to do something with it. So the calculator that I recommend that you use would be the Desmos calculator, the one that we've been using. I'll say all semester, even though it's a very young semester at this point, right? But what I try not to do on a test is have you work with a ton of different types of data. You know, so it's, you see that you have that one data set, another data set, and one last data set. It's not, you know, there's 10 questions. It's not going to be a unique data set for every question. We're going to refer to the same data set a few times. So with that in mind, you got to be really careful about how you type in your data, right? You got to make sure it's in there correctly because a lot of questions will, the quality of your answers will be determined based off of how accurately you type in this information. All right, so I'm putting a lot of emphasis on typing it in correctly, which of course means I'm guaranteed to screw it up. So, it's like when I used to coach basketball, I would tell my players, all right, listen, this is how you shoot a ball properly. You got to keep your elbow in, you got to elevate to the highest point. And if you do that, you know, you bend your knees, you do all the mechanical stuff right, you'll never miss that shot. Like so. And then I demonstrate, and of course it would be an air ball or a brick, or it wouldn't be a bucket. That's the important. It's always a miss. All right, so I typed the data in. Now it's a matter of making sure I typed it in correctly. I always check it, and I mentioned this before, but it never hurts to say it again. I always check my data in a way that's different from the way that I typed it in. All right, so I typed it in top to bottom, so let me check it bottom to top. All right, so I mean, I don't know if there's any psychological thing there, if there's like left side of the brain, right side of the brain, prefrontal lobe, parietal lobe, any of that crap going on. I just know that it requires me to think a little bit differently. And in doing so, if I'm going to catch a mistake, it's probably going to happen using something along these lines, that kind of thing. All right. So, number one, create a frequency table and a frequency histogram for the data. So there's a bunch of different ways you can do this. We've done it by hand. We have videos for that. You can check that out. But it's test taking time. You know, like when it comes time to take a test, it's like, yeah, we can do it by hand. We got all the theory, but now it's like, okay, show me the shortest, quickest way to get this done. Right. So that's what I'm going to do. So, and let me preface everything I'm about to say by saying that I accept Desmos work just as I would handwritten work. All right. So anything in Desmos calculator, if you submit that as your work, that will be accepted just as if you hand wrote it yourself. All right. I don't need you to write down or type in data on a Desmos calculator to just reproduce it on paper to submit it. All right. So I'll show you how to share that also. All right. So we have our information in X1. Wonderful. I want a histogram. Now we know from Desmos that there's a lot of functions that's stored in here. But if we also know that if we're in doubt, type the name of the thing that you're looking for. And if Desmos can do it, it'll tell you whether or not it can do it. So it's asking me to do a histogram. So let me do that. Let me type in histogram. Well, it went from italics to regular font. So that's usually a good sign. That means that that's a command that Desmos has. Now you see that little triangle with the exclamation point? If you tap on that, it usually gives you some indication of like why it's not doing anything. Histogram is a function. Try using parentheses. Will do. Now it asks you for the data set. Well, my data set was in X1. It created a histogram. Oh, look at that. So you have three types of histograms that Desmos will compute for you: a count, which is the frequency histogram, and then relative frequency histogram, relative frequency histogram, and density histograms, which are PDFs or curves, like a normal curve. This is all I need. So it says create a frequency table. That part we need to do, but create a table and a histogram. Well, we have the histogram, so we're good there. Now it's just a question of whether it's a histogram that I like. This has a data set of X1 that goes by, when they say bin width, they're talking about the width of the intervals. They're saying go by ones. I don't like the sound of that. Like our lowest value here is 0.93. The largest value is 27.51. We want to have at least 5 intervals. That's something we always want to keep in mind. Whenever we create a histogram, we always want to have at least 5 intervals. All right. So what I'll do, and you can do this a couple of ways. I can tap on that little 1. It happened so quickly that you might have missed it. All right. So let me do it again. I'll type in histogram. A histogram? No, histogram. All right. It autocorrects from italics to ordinary font. So that tells you that you're on the right track. I have the X1 in here. Now you see right next to that bin width, it says equals 1. I tap on that little equals 1. And what it did was it transformed my notation. And it made my X1, histogram X1, into histogram X1 comma 1. So what that 1 is after the X1, that's the bin width, right? So I can make this number anything I want. I can make it a 5, to make it wider bins. I can make it 2. I can make it 10 if I want to go crazy about it. Or I could just leave it as is, right? Either way, it's going to be okay, right? I could also change the alignment of my bins. I can make it aligned on the center or to the left. We like a left alignment, all right? So these are the settings that we want. This one, that one, it could be whatever you want, but we want to have it aligned to the left, all right? So then what's happening is each one of these bins has a width of 1. And the histogram has been completely constructed, accounting for any value. That first box, that first bin would be between 0 and 1, then from 1 to 2, then 2 to 3, 3 to 4, 4 to 5, and so on. All right. And then it goes on and on and on until we cover the entire set. Now, if you don't like that, again, like I said, maybe you want it to be a little wider, maybe make it 5 so that you get a little bit more interval out of this. All right. And then it's just a matter of getting the heights. You know, so in that regard, it's really, I mean, estimation more than anything else. But what a lot of people will do is they'll use this information, and I'm going to go with the intervals of 5. They'll use the information from the Desmos calculator to kind of get them started, and then construct it on paper based off what they see there. So they'll say, okay, well, 2, 4, 6, 8, 10. It looks like my vertical axis is going by 2. So 2, 4, 6, 8, 10. And then so 12, 14, 16. So 2. Oh, 46, geez. It's been a special kind of day. And then we're getting 2 bins between 0 and 10. So that means we're going by intervals of 5 here, right? So 5, 10, 15. These are the markings. I'll show you how that translates to intervals in a second. All right, so these would be my X values. So the first one, 12, 14, it goes up as high as 15. Then the second one only goes up as high as 2. Then only as high as 1. Then we get no height, then eventually it goes up to 1 again. You just kind of eyeball it there. So 15, you can check the numbers in there if you want. 15, 2, 1, throw a couple of zeros here, and a 1. Now, in terms of the intervals, it's really just a matter of knowing that this is going from 0 to that 5 is the cutoff that starts the next interval. So this is going from 0 to 4 and change. So this is like saying from 0 to 5 to less than 5. So that's what this interval is really talking about here, right? So this interval here is saying from 0 to less than 5. And the next one would be from 5 to less than 10 and so on. But I don't really need you to write that because like I said, when we were talking about this as part of lecture, it was one thing. It was for the purposes of theory and understanding and stuff like this. Now we want the most efficient way of getting a graph completed, right? So you can get the table out of this also. 0 to less than 5, 5 to less than 10, 10 to less than 15, 15 to less than 20, 20 to less than 25, 25 to less than 30, and then just put in the appropriate numbers, 15 to 1, 0, 0, 1. So those are our X values and our frequency. All right. So that's assuming you wanted to do it by hand, because again, I got to operate under the assumption that 50-50 I was talking about before. It requires me to take a little longer, but some people want to do it by hand and some people want to do it in the calculator, right? So I just do what I can, right? But as far as the histogram is concerned, if you just want to submit your Desmos work, you can do that. The only thing that you would really need to do, you got to have an account. So that's the first thing. I recommend that when you save your work, you give your graph a title. So this would be, how many statistics tests have you taken? I don't know. So it's probably okay to call this statistics or stat unit 1, question 1. Hey, maybe throw your last name in there, make it a little bit more helpful, and then save it. Then, so you got to have an account. So create a Desmos account if you haven't done that yet, and then create a share link. And then in Blackboard, in that whole share field that I was talking about before, well, I call it a share field, but it's, where you can type an answer. Just put your link.
Oh.
All right. So you wouldn't have to create the graph by hand, is what I'm saying. All right. Oh, thanks, Mohammed. Appreciate it. I'll get you for attendance. All right. So what I'm saying is it's either, and this has been a kind of a sticking point in the past, it's either your Desmos link or construction of the graph. Not both. You don't have to do both, right? So once you come up with a histogram here, you're good. The only thing is a histogram has to have appropriate labels. Now the numerical labels are fine, but we need qualitative labels. You see I have X and F. So you tap on that little wrench there, and you could see under X-axis and Y-axis, it has all the numbers. It also says add a label. So for X-axis, I'll say, well, I'll put an X there. For my Y-axis, I'll put an F. And now I have the appropriate labels, all right? They're kind of hidden away there, but they're there, and that's all that matters, all right? So creating the share link is really all it takes to get credit for a graph, all right? And if you want to consolidate and put more than one graph on the same Desmos, that's fine. But you would just paste the same link into the answer field for two different questions, all right? So I'm trying to make this as accessible as possible to everyone, because I know some people are more tech-minded than others, but I don't want people who are not tech-minded to feel like they're at a disadvantage. I mean, it's easy enough to create the graph. For the folks who look at Desmos and say, well, that's so confusing, I'd rather do it by hand. There's just as many people that are like, why the hell would I ever want to do it by hand? It's so much easier to do it on a calculator, you know? So it really is a 50-50 split. So I want to make sure there's something for everybody, all right? So that would be your histogram. Now, as far as the table is concerned, on Blackboard, in that answer field, there is the option, there is the ability to type in a table, all right? What I found is that some people don't want to do that, and so they'd rather handwrite that, and so they put that as part of the question 11, the handwritten upload, and that's fine.
Can you show us where you can do that in Blackboard, or you show?
Yeah, let me show you real quick. That's what I was showing before. It's the same field. Let me I'll record this. All right, so in the answer field, you can see that you got all these different options here, but one of them is to insert a table.
Oh, okay.
And you just put in the parameters of the table. I don't think you need to go too crazy in terms of columns and rows. You really just need the 2 columns. I think 2 rows gets it done. At least that's my preferred approach. It'll create this like really narrow, nonsensical looking one, but it expands to fit what you need it to. So then you would type in, 0 to less than 5, then 5 to less than 10. It's a pain in the ass. I'm not gonna lie.
It looks it.
but it's still in lieu of actually handwriting stuff. It's still an option,
Okay.
But like I said, it expands to fit.
So the other option is to do it in Desmos and just paste the link.
And then just paste the link. Yeah, exactly. It looks like I see a question coming in. Can we screenshot our answer on Desmos? That's fine too, if you just want to do a screen capture. The only issue I've run into on that one, that comes down to security more than anything else. So that's the only issue I've had there. Okay, so that's the histogram. Now the box plot, great news. Desmos is also going to take care of that for you, but I'll again show you how you can do that by hand if you want. One thing that you're going to need to do regardless on Desmos is figure out the 5-number summary, right? So that's under functions, stats, right? So function, stats. Well, it's funcs. All right. You still got to tell Desmos where to find the data. So you tell it it's in X1. And what it'll do is it'll produce the 5-number summary for you. So 0.93, 1.21, 1.63, 4.86, and then 27.51. All right. Now, when it comes to plotting this by hand, again,
I got a question. That is from the graph, right?
Say it again.
That is from the graph, right? The summary.
The 5-number summary is for the box plot. All right. So when we type in stats x1, it gives you the 5-number summary. And that we're going to use to create the box plot. Yeah. So I won't harp on this too much, but I will say this one last time. Again, I'm going to show it by hand, and then I'll show it on Desmos so that, you know, each type of individual, each type of learner can get a little bit of something out of this. Right? So what we want is a numerical scale going from some clean number, round number, less than the lowest number, and a round number that's greater than the largest number, right? So that the cleanest number nearest to 0.93 would be 0, right? And the cleanest number nearest to 27.51 would be 30. And so what I want to do is break this up into even increments. So if I split it right down the middle, that'll get me to a 15. If I break the interval of 15 into thirds, I can get 5, 10, and then 15 to 30, I can break into thirds again, 20 and 25. And so now I have a nice scale getting me from 0 to 30, right? So what I do is at some predetermined height, whatever you like a centimeter above the number line, plot those points. So 0.93, and you're just estimating 0.93, I put it about right there. 1.21, I don't know where that is, but I do know it's got to be a smidge to the right of 0.93. 1.63, smidge to the right of 1.21. You know, you can kind of finagle it a little bit, maybe move it a little bit closer, you know, move the points closer to each other, move them closer to 0, whatever. But as long as they look like they're in the neighborhood of where they ought to be, then you're fine. The 4.86 should be really close to 5, just shy of it. And 27.51 should be about halfway between 25 and 30. Now, a box plot has a box surrounding the middle 3 points. With a vertical line passing through the median, if it'll let me, and extending out to the extreme values, right? The lowest and highest point. So in this case, the lowest point is actually really close to the lower quartile, but the highest point is really far away. So that's essentially what your box plot is going to look like. All that being said, if you don't want to do it by hand, you don't have to, although that is a work of art that I just produced right there. If you want to do it on Desmos, you need only type box plot. See, it goes from italics to regular font. That's how you know it's a command, a Desmos command. Then type in where you can find the data, or where Desmos can find the data. And it asks you for a couple of things. It asks you for an offset, a height, and whether or not you want to exclude outliers. But by the way, that's it telling you that it'll figure out outliers for you if you want it to. Right? We don't want, when we're asked to create a box plot, we do not want to do that. So we leave exclude outliers off. The offset, that's really up to you. Right? What I don't want to do, if I'm graphing this simultaneously with my histogram, see, I have it on the same Desmos. If I were to have them both on at the same time, they would interfere with each other. I don't like the look of that. So what I can do is I can offset my box plot so that it's nowhere near where the histogram would be. So maybe like -5. You know, what that'll do is it'll shift it downward 5 units. All right. This way I could actually run my box plot and my histogram at the same time. It looks nicer. All right. Also, the height. It's kind of like a little skinny little box there. So I don't really see all the bits and pieces. So instead of having a height of 1, maybe I'll do like a height of 3. See, it kind of makes the box bigger. It's discretionary. You can make it whatever you want. Let's say you wanted to make it 30. I mean, that would be foolish. Look at that. That looks ridiculous. But you could technically do that if you wanted to. 3 looks fine. I mean, you make it 5 if you want, but I think 3 is reasonable, right? And now you have pretty much what you have with the hand-drawn box plot, except you didn't have to do anything, all right? Now you may look at it and say, well, what about this? I see the space between the end of the box and that purple line. And then I would say, well, it's actually the same thing on the Desmos box plot, except you kind of have to get in to see it. It's there. It's just zoomed out sufficiently far so as to make it difficult to see it. But we have everything we need. We got a nice looking histogram and a box plot all in the same grid, all in the same graph. So when you go to share this, the first thing you do, for the love of everything you believe in, don't forget to save it. Now it's questions 1 and 2. You know, retitle it. If you have every intention of doing as many questions as you can on the same Desmos, then just call it stat unit 1 and your last name, and then change it later on. But question 1, question 2, you know what I'll do? I'll keep it open. Question 1 through question, I don't know yet. We'll see. We'll put it in later. So save it, and then create your share link. Every time you save, you'll need to create a new share link in order to send the updated information. Unfortunately, there's one flaw about Desmos. It's not like a Google file where you create the share link and then every time you change something, it changes synchronously. It's not like that, right? Every time you make a change that you want me to see, create a new share link and submit it, all right? So when you're done with all your Desmos work, you could just paste the same link in for any question on Blackboard that answer would be relevant for, right? Like, for example, number 3, actually numbers 3, 4, 5, and 6 are all referring to the same data. So maybe you do them all on the same graph. I don't know, we'll see, all right? Or on the same Desmos. So we can leave this stuff on until we have reason to turn it off, but I do need to figure out the mean of the data set. So function, stat, that one's obvious. And so it's all in the funcs. Stat menu. So mean is easy enough to find. Type in your X1. 4.462. Just follow the rounding instructions on the test. It'll vary from question, not question to question, but it'll vary sometimes. Sometimes the numbers will be nice. Sometimes they won't be. And when they're not nice, I'll say round to the nearest 10th or 100th. Or if I don't say to round it, then you can round it any way you want. Just whatever method you choose for rounding, just make sure you do it correctly. Right? I've mentioned this before. I know I have, that in the past, I've told people, round it any way you want as long as you do it correctly. A student will say that they rounded to the nearest 10th and they don't know why I took off points. You say, well, they rounded to the nearest 10th, but they wrote 4.46. That's the nearest 100th. You said you were going to round to the nearest 10th. You didn't do it the right way based off of what you said you were going to do. All right. So just be careful of that kind of thing. The median we already have. That actually came up in our 5-number summary, 1.63. The range is the difference between the highest and lowest value. So the max minus the min. So we got to figure that out. So that's going to be 27.51 minus 9.3. So if you really want this to be like a standalone submission where you don't really have to write too much down on Blackboard, what you can do is you can insert a little note here and say that this is going to be the range. And then right below it, the computation for the range, 27.51 minus 0.93. And so now you have the range. You can also write it down if you want. These numbers are easy enough to type in. And in fact, there'll be fields for you to type these answers in, but there's nothing wrong with having it all on Desmos too. Just in case you screw it up, you write the wrong answer down on Blackboard, at least you have a record of what you did. I could look at that and say, well, okay, I see what you did wrong there, partial credit. Right? Like for example, in the mid-range, some of you might need some partial credit for that because the most common error on this test happens for this particular question. To figure out the mid-range, it's max plus min divided by 2. So it's the average of the maximum and minimum values. All right. So I'll make a little note here, mid-range. So I'm going to do 27.51. So I used the division bar first, 27.51 plus 0.93 divided by 2. And that gives me my mid-range of 14.22. But students who don't study or don't take good notes, let me just make sure I did that right. Yep. They often think that the mid-range is just half of whatever the range is. Well, the range is this, cut it in half. That's probably what the mid-range is. Well, it's not. So you just threw away a point. However, if you show me the incorrect work leading to an answer that's consistent with your incorrect work, I can still give you a little partial credit, give you a little something for your trouble. That's the way I look at these things. All right? You took the time to try to come up with a reasonable answer. You got it wrong. It's still worth something to me. I'll still give you a little something. Not going to get full credit, but you'll get something. All right. Sample, variance, sample, standard deviation. When in doubt, take a look in that functions menu under stats. You know, if you see it, it's there. Great. If you don't, well, you're out of luck. No, well, standard deviation staring right at you, right? You have standard deviation and standard deviation with a P after it. P is for population. That's unit 2. We're not even touching that yet. So standard deviation X1 is what we would type in. Round that, I'll do it to 3 again, 3 decimals, so 6.609. All right. Now the sample variance is the standard deviation squared. So this is what you get if you take the standard deviation of X1 and raise it to the second power. All right, so just do that. That's easy enough. But again, if you want to have some good looking work here, what you can do is throw in a little note that this is your sample standard deviation. You use abbreviations, those are fine. Oh, it's out of order. What am I going to do, Master Skywalker? You see that little quote there? Just drag it up, and you can swap some things around. All right. So then the next one would be variance. I'm doing it a little out of order from the way the test is asking for, but that's just because I'm getting my variance based off of my answer for standard deviation. All right. So I type in variance here. Now, a nifty way of handling this would be to tap on this little gear icon. When you tap on the gear icon, it gives you an option to copy. All right. So if I tap on the copy icon right next to the X, or a duplicate icon is what I should say, it'll bring up the same command a second time. I can drag it down underneath variance and just slap on a power of 2. So now I have the right answer, 43.684. But I also have some supporting work. This way, again, if I screw up something, maybe I typed in the data incorrectly. Heaven forbid you type in the data correctly. All of this would be wrong. Every single question. Are you going to get a 0 on the test? No, because you submit all your Desmos work. I look at it and I say, oh, you typed it in wrong. Everything's right based off of that mistake, though, minus half a point for typing in the data values wrong. You can get every single question on the test wrong based off data entry and still get like a high A, right? So all because I'm able to go through your work and see where you made a mistake. Now, if it's a conceptual mistake, as in you didn't know what the heck you were doing, that's a different story. But if it's data entry and you give me your work, I can always figure out where the error is. Now you'll see here that I bypassed part C there. The mode just kind of glossed over it as if it didn't exist. And there's a reason for that. As far as Desmos is concerned, it really doesn't. Now, we don't look at Desmos as our tool for finding the mode. We look at ourselves as the tools for finding the mode, right? So what we're going to do is just go through the data set and look for the value that seems to occur more than any other value. So we're essentially looking for repetition. Now, as I work, and I'll be nice when it comes to tests, I tend not to be mean about things. I'm going to give you the data set in order. I'm not going to give it to you out of order and make you go through that, that obstacle course. But when you look at it from top to bottom or bottom to top, if there are any repeated values, you should be able to pretty easily pick it out. I don't see any values that occur more than any other values. Every value here is unique. And so therefore, we can conclude that there is no mode. All right. And that's again because no value occurs more than any other value. All right. Now, you could have multiple repeated values. It's the one that repeats the most. All right. Just because a value repeated or is repeated doesn't mean it's the mode. It has to repeat more than any other value. All right. So you can see what we have here on paper compared to what we have on Desmos, and you can see that a fair amount of the stuff that we wrote down on paper, in fact, I would even say the hardest stuff is stuff that Desmos did for us. And so if you want to kind of really make it one-stop shopping on Desmos, put a little note in there saying mode, no mode. Mode is this, there is no mode, or whatever, depending on the situation. All that information, if it's in Desmos, that's good enough for me. The more organized it is, the easier it's going to be for everyone, but it's a good thing. All right, but again, constantly save and then share, create that share link and paste it into Blackboard whenever you think you have the solution to a problem. All right. So number 4, determine if the data are normally distributed. Show all work or include a detailed explanation. So if you remember, we had, and you may not remember all the specifics, but you might remember that there was the not so bad way, and then the way that took up like half of a class to do. That involved the table with the z-scores, and it was like, whoa, that one's intense. This one, okay, it's not the greatest in the world, but it's still a lot better than that one. Again, day of the test, you want to be going for the way that is the quickest and easiest way to get to your final answer. All right. Efficiency is what we're going for. All right. So what we're going to use is the empirical rule. All right. Now, the only reason that we're using any rule is because it said show all work or include a detailed explanation. I'm looking at a graph that clearly is not normally distributed, right? A normal distribution would have a bell-shaped look to it, right? So it would look something like this. We're still referring to that original data set. Whether you're looking at the histogram or the box plot, there's definitely a great deal of skew to this. In fact, if I had to graph this just using a curve, it would probably be something like this. You know, this is really what we're looking at. This guy over here, not this one. So we know going in that it's not going to be a normal distribution. It's just a matter of making it all come out in the wash. So we need two pieces of information. We need the mean, and we need the standard deviation. We know them both. We had to figure them out already. The mean was about 4.462. The standard deviation was about 6.609. All right. So for the empirical rule, what we want to do is we want to compute, where necessary, 1, 2, and 3 standard deviations about the mean. All right. So the first computation is x bar minus 1s, comma, x bar plus 1s. All right. So I'm just kind of looking at this Desmos calculator as a running log of all of my work, right? So what I'll do is I'll just write in here a note, empirical rule. Or you could even say question 4 to indicate that you're moving on to a different part of the test. We're looking at the first case, which is the x bar plus or minus 1s, but it's really one standard deviation away from the mean. All right, that's my first computation. All right, so it's going to be 4.462 minus, I'm going to type in the 1. We talked about this when we actually did it the first time, a couple weeks ago, though. I type in the 1 because I'm going to duplicate this and change the 1 into a 2 later on if necessary. All right, so that would be my low bound. All right, so x bar minus 1 times s would be negative 2.147. Then I hit the little gear icon to duplicate, and I change the minus into a plus to get us to 11.071. All right, and so what we do is we count up the number of values between these two numbers, and divide by the total numbers in the set, divide by total number in the set, divide by total number in the set. If it's close to 68%, so that's plus or minus 2 percentage points. Like I said, chose. Then compute x bar minus 2s, x bar plus 2s. If it's not, then you stop and you say it's not a normal distribution. All right. So I'm just going to shrink this diagram, move it up above. I'm going to get rid of this one because it looks ridiculous. I'm going to shrink this all down in a sec to save some space, but what I'm going to do is I'm going to copy this over to the first page, this computation, this set of computations, so that we can actually count some values. All right. So I'm looking for the total number of values that are between negative 2.417 and 11.071. All right. So in this data set, I'm just going up the line, up or down the line, and saying, all right, which values are within this interval, right? Well, not the first two, but everything after that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 values. Out of 19 are in the interval. All right, so that's 17 out of 19 times 100. If that's close to 68%, which it won't be, based off of the size relationship, like 90%. If it was close to 68%, we would go on with the second computation, but it's not, all right? So this is about 89.47%. That's not near 68%. So therefore, the 3 dots in the form of a triangle means therefore, we're looking at something that's not a normal distribution. All right. So I'm going to move this back to the other page, clean things up, but that's the process. All right. You're kind of rooting for failure here because it's less work, but you kind of know going in what you're up against. It was skewed. It had a right skew to it. It was, all the data was on the left-hand side, a couple of values on the right-hand side, and that was it. You know, and the tail, look at the size of the tail in the box plot. There was no way this was going to be a normal distribution. It's got to be symmetrical if it's going to be normal. And that's not the case here. Right. So because it's nowhere near 68%, we would say that this is not a normal distribution. Right. Now, if we got something that was close to 68%, then we would go through the whole process like we did in class. We would do, you know, instead of X bar minus 1s and X bar plus 1s, we would do X bar minus 2s and X bar plus 2s and go from there. But as it turns out for this question, it's not necessary. All right. So let me just resize some things here, get it all in. All right. So then we get into outliers and unusual values. Now I'm actually going to do the unusual values part first because that actually goes hand in hand with what we just did. All right. Unusual values are outside the interval of X bar minus 2s, comma, X bar plus 2s. So what I would do here, again on Desmos, little notation, just kind of swing this down the line here. Little notation where I just say unusual values. And then I would just take my previous computations, you know, the 4.462 minus 2 times 6.609, duplicate that. But then change the 1 into a 2. And then I could duplicate it again and change the minus into a plus. that's assuming you don't want to just retype it. Sometimes it's easier to just retype it than to think about where you can get all these values from again, right? But the unusual values would be based off of these numbers. Since it's the same data set, it's the same mean and the same standard deviation, makes life a lot easier, right? So we're looking at values outside of the interval of -8.756 and 17.68. So I'm going to go back to my original data set and just see if there's any values that are not in that interval. So I take a look at my data set here and I say, okay, well, any values that are not outside this interval. All right, well, it looks like the only value that's not outside the interval here, or I'm sorry, that is outside the interval, is China at 27.51. All right, so the global emissions, the unusual value would be the 27.51%. All right. So the only value that's outside of that range would be 27.51% is unusual. We also have to determine outliers. Now, outliers is a tricky thing because Desmos will do it for you, but then you run the risk of reporting the incorrect box plot when you submit your Desmos work. So when you tap on, remember all the way back when we had box plot here, it said exclude outliers. You tap on that, and what it'll do is it'll identify the outliers for you, right? So you look at it and say, well, these two dots here represent my outliers, and you could just tap on them, right? What we have here is known as a modified box plot, and so what I'm going to do is I'm going to just do a quick screenshot. What a lot of people will do, and like this is not the most tried and true thing ever because I've only started using Desmos in this course last semester, but it seemed to kind of work out. But varying degrees of success, and that is some people will save a brand new file that they have all their extra stuff in, and that extra file would be just like the weird things that they thought conflicted with their initial submission. So they submit this Desmos file for most of their work, but then every now and then they come across a problem where they're like, well, if I submit this here, it'll conflict with that. So let me just create a new Desmos for it. So they duplicate the Desmos and just delete all the stuff they don't need. So that's fine. The benefit of doing this is if you do a screenshot and just submit that, in a Word document or something, you can tap on these points. By tapping on them, it'll identify the outliers, right? What we have here is known as a modified box plot. All right, so we can conclude that 14.75% and 27.51% are outliers. All right, and the justification is very nice. The justification is the modified box plot. The problem is I can't submit this for full credit for number 2 because this one was just asking for the box plot. So what I have to do is get what I need from the modified box plot by checking exclude outliers. When I'm done with that, then I uncheck that so that it's back in the appropriate form and save it the way it needs to be in order for me to get credit for the appropriate box plot. All right. So the alternative to that is to save and retitle it You know, you see the option to duplicate the graph. You can call it modified box plot and submit that as a new link and just delete everything that you don't need. So, okay, we don't need this. And, you know, the only thing that's relevant here is the modified box plot. So I get rid of literally everything else and then create a share link for this. So that's the playing it safe approach, right? But you got what you need here. There's your modified box plot. You save it as the modified box plot, and then you just share that link, right? Get yourself a new share link, if it'll let you. And just go that route, right? And then just go back to the other file that you're working with. You know, you can, like, when all is said and done, on this test, you might have like 5 or 6 different Desmos calculators that you're submitting. It's all fine by me, right? So, you know, it's just a matter of how you want to organize things. But anytime you submit or come up with a new data set, you might as well just create a new Desmos calculator, because otherwise you're really going to start getting your wires crossed. So in number 7, again, it's asking for us for the mean and standard deviation, 2 different data sets. So I'm going to create a new Desmos here, new blank graph. I have 2 data sets, so I'll put them in 2 different columns. I got 5833.49, 5966.46, 6097.75, 6056.31, and so on. All right, so that's my first data set. The second one, 3624.29. Trying to not go cross-eyed in this process. And 4171.18. All right, so double checking. That's the name of the game here. So, okay, good, good. And it looks like it's all incorrectly. So for this one, the first 2 parts of the question, very straightforward. Find the mean and standard deviation for the US and then also for the European Union. All right. So US, European Union. Well, the US I put into X1, the EU I put into Y1. So we'll have to keep that in mind. So might make a note here that we're working on the US at this point. So then function mean X1. So X bar in this case 6033.966 really, if we round to 3 decimals. All right, we need the standard deviation. So function standard deviation x1, 132.735. All right. Then we got to do it all again, this time for the EU. All right. So the mean, this time it's y1. So you could say y bar here, because we have a y variable, we could say y bar. And S for that particular variable. You could say X bar again too, it doesn't really make a difference. The bar is the important thing. So 3805.544. And the standard deviation of Y1, so 205.454. All right. So that's all we needed for A and B. But then part C, that's the weird one. Which location had worse emissions relative to their own 7-year average? We'll get into what constitutes worse, higher or lower numbers in a sec. The US or the European Union in the year 2016. So where's 2016? Over here. These are the two relevant values that we care about. What we're asked to do is find the z-score. Right, so the z-score for the US in 2016 and the z-score for the European Union in 2016. All right, so the particular value is 5,833.49. From that, we're going to subtract off the mean, because remember, just kind of jot this off on the side, the z-score formula, X minus X bar over S. All right. So 6033.966 over 132.735. And then on the other end, we're looking at 3624.29 minus the corresponding mean, which would be 3805.544 over 205.454. And so we can get our two z-scores, and we would just compare the two and see which one constitutes a better number. All right, so we got to crunch these numbers. All right, so fraction 5833.49 minus 6033.966, 132.735. So we're looking at about negative 1.510. And then for the European Union, 3624.29 minus 3805.544. So we're looking at about negative 0.882. All right, so we're looking for a conclusion here of which one indicates a better value. All right, so it's just a question of, well, do we want higher levels of greenhouse gas emissions? Is that considered a good thing? Do we want to be above average? Probably not. All right, so we're looking for the smaller number. Smaller number would indicate a better outcome. All right, so therefore, we dodge in the form of a triangle means therefore, the EU it said actually which one had worse emissions. So the US had worse emissions relative to their own 7-year average. Right. And that's because their z-score is lower. Right? It's more negative than the negative 0.822. And so that's indicating that that their value is a lower. Actually, sorry, I think I just got that backwards. Worst emissions, no, it would be EU. Sorry. Worst would be a higher number. Right? Because if it's greenhouse gas emissions, we want that to be low. Right? We don't want that to be a high number because we don't want to destroy the earth. So we're looking for the one that has a lower number to be better. So this is better because it's lower. All right. So it's like golf scores versus basketball scores. So it's a case where the lower score wins. You know, that's what's happening here. We want it to be lower. We want to have 0 greenhouse emissions. We don't want to have any. We'll settle for something that's below average. Right? So US was better than EU, which means that EU is worse. Right? And so the last problem, I know we're kind of coming up against it, but it's going to help you for the test. So it's kind of like you just kind of grin and bear it. But in terms of that last question, it's kind of a lot to do in terms of data entry and stuff like that for not so much of a payoff. So on the test, I can tell you that what I tend to do is, again, minimize the amount of times you have to type in data. So you can expect that to be part, that question to be part of another data set. Right? You wouldn't have to type a unique data set in for that. It's just too much of a time waster. Right? But this one, it's 2 unique variables compared to one another. The following data represents total greenhouse gas emissions for the world since 2010. The units of measure are metric tons of carbon dioxide equivalent. So I'm just going to very quickly save this as Q7. And I'll put that in the notes later. But here we need a fresh new data set. You got to type them all in. Fortunately, and you'll see this as we go, 2016, it's the year since 2010 for the world since 2010. That's a typo. That should be the world since 2000. As you can see by the data set, it's very clearly going from 2000. So 2016, 2015, 14, 13, 12, 11, 10, so you can see it starts auto-filling it for you. So that's kind of a little bit of a time saver. The other values you do have to, unfortunately, type in, right? And unfortunately, real data sometimes is lengthy. So the trade-off is I won't ask you to type in too many times overly lengthy data sets, but it could be that you have multi-digit things, values that you have to type in, and sometimes that's unavoidable. Right? So you just kind of grin and bear it. For 8.77. I typed in the wrong one there. So 2009 should be 44936.19. 44952.57. 44584.43. Back in my day, we had to do all this without a calculator. That's not true. Honestly, the guilt I'm feeling here is almost overwhelming. Because I actually gave this was a test. I don't remember this data set being so long, but I guess it was. Could be why most of the class got it wrong. 420.79. Okay. We'll say a prayer for him. Who am I kidding? I gave them all like 20 bonus points throughout the course of the semester, so I'm sure it all worked out. Oh, it's great when that stuff's getting recorded. So anyway, determine the line of best fit for the data set and estimate the year that the metric tons of carbon dioxide equivalent reaches 50,000. All right. So what you're going to type in for a line of best fit, because again, we're at the point where it's just like, we got to get it done. So you type in y1 tilde a plus b x1. All right. So this is the line of best fit. So y1 tilde a plus b x1. So that's the model. And what we need to do is estimate the year that the metric tons of carbon dioxide equivalent gets to 50,000, or would be 50,000 based off of this model. All right. So first thing we're going to do is we're going to get this information down. Fortunately, again, if you like Desmos, then you've already got the information down. You don't have to rewrite it. It's all there. All right. You just got to do the work in Desmos to get your solution. But if you need to get it down on paper, you need to get it down on paper. Y hat would be equal to negative 1.5197 times 10 to the 6th power plus 779.103x. All right. So on Desmos, we need to do a couple of things. One, it'd be nice to be able to actually see the picture. So we pinch zoom outward until we see something. And then we see this big old mess here. That's where most of the points are. That's clearly not a good looking graph. So what we do is we tap on the wrench and adjust our x-axis. We want to go from, like, instead of whatever this is, we want to go from 2000. 2020 ought to do it. And then for the y-axis, it looks like the lowest value there is just a shade north of 37,400. So what I'll say is, I'll go 30,000 to like 50,000. Yeah, it gives a little bit of a better look, right? And also you can see that it's not really a linear model that would be the most appropriate fit based off of this diagram. But, you know, that's the question's asking for a line of best fit, so that's what we get, right? Now, what we need to do is figure out when this is going to be equal to 50,000. So what we do is we type in Desmos two equations. One, brand new equation, y equals a plus bx, right? So basically what we just typed, just without all the bells and whistles. So y equals a plus bx, right? And you'll see that that's the same line. The thing is, this one we could actually perform operations on, the other one we can't, all right? Then we also type in y equals 5,000, because we want to know when the metric tons of carbon dioxide equivalent gets to 50,000, which is a measure of the y value. These are our x values, these are our y values. We want to know when the y values are going to get to 50,000. So I type in y equals 50,000. And then what we do is we find the intersection. All right. So we get that by just kind of getting in as close as we can so that we don't accidentally hit the wrong point. Tap on where the two lines cross. You'll see a gray dot appears. Tap on it a second time, and it'll give us that intersection. All right. And so that intersection, let me just kind of clean this up a little bit. That little intersection would be at 2014.748, comma 5,000, or 50,000, I should say. That's correct. So estimate the year. So it would be in the year 2015, because 2014 would already have been completed. We'd be in the year 2015. Yeah. So, and it is an estimate. So if you just round it, you'll get there. You don't really have to overthink that. Right. So an estimate would be like around 2014, 2015, we'll do it. You know, I mean, you could look at the data set and it seems to be pretty consistent with that, but it's a little iffy. All right. We also need a residual plot. So that would be number 10. In addition to what we have to do in number 9, which is the other types of models. So let's actually do the residual plot first, because that's easy. You just tap on the word plot here and nothing happens. No, it happens. It doesn't happen here. It happens down by the x-axis. So what you do is you zoom out until that second array of points appears, and you take a look at that. This is your residual plot. It'll always be centered around the x-axis. And how that residual plot manifests will determine whether or not a linear model is appropriate, right? And so here, it's pretty clear, you know, if definitely study the notes if it's not. I hit paste. Oh, okay, there it is. It should be pretty clear that a linear model is not appropriate. Because there is a pattern in the residual plot. All right, so if there's any kind of pattern in the residual plot, it means a linear model is not appropriate. All right, very important. So then, you know, 8 and 10 are accounted for, and that's all well and good, but then we got to do this other type of regression. So we'll do that. So this is question 8 and 10. I'll organize this in a more reasonable fashion later. But what I'm going to do is I'm going to make this a separate Desmos for question 9, save it as a fresh new one, and get rid of all the stuff I don't need. For example, this E column, I don't need that because that was the residual plot. I can get rid of all that information. I don't need this information here. I'm going to need the linear. They want me to evaluate the R squareds for the linear, which we have. And it's the R squared value that's going to be closest to 1 that we're looking for. That's the winner. So the R squared value here is 0.967. So what I then do is I look for a quadratic regression. Right? So the quadratic regression, the model that we use is the quadratic equation. This is all in your notes. Y1 tilde AX1 squared plus B X1 plus C. All right. So that's what a quadratic model looks like. So that's what we're using to represent the quadratic, and you can see that the R squared value is a beefier 0.987. All right. So we're getting closer to 1. So linear is not going to be the winner. We knew that because of the residual plot, but now we also know that because it doesn't have an R squared value that's as good as the quadratic. So next up on the list would be the cubic. So Y1 tilde AX1, now it's cubed, plus B X1 squared plus CX1 plus D. All right. And again, I'm going to share all these Desmos calculators with you. I'll put it in the announcements later so that you can copy paste and have it. But this is what you would type in for a cubic regression. So 0.987 again. The other one was 0.9872 also. So now it's like, well, which one's the winner? So I'm going to put them both down as 0.9872. So it looks like we have a tie. Let's see if the exponential is going to be the tiebreaker. If not, we got to make a choice between the quadratic and the cubic. So then what I would do for the exponential is Y1 tilde A times E raised. Oh, you know what? Sorry. I just want to make sure, because I do it differently in each class. I want to make sure I used, or make sure of which method I decided to use in this one. Yeah, okay, so the EBX one, okay. So, no, because I use common logs in another class, and I'm getting old enough now that I'm getting my classes confused with one another. All right, so we're using the base E in this one. So 0.9554. All right, either way, it ended up not making a difference because that wasn't going to be the winner anyhow. All right, so we know that this one didn't win. So our choices are quadratic or cubic. The tie goes to the simpler model. All right, so the choice would be a quadratic regression. Because it has the same R squared as cubic, but is a simpler function. And in fact, if you're really making decisions based off of this in the real world, you would actually go with the linear case because you'd be willing to sacrifice a little bit of accuracy for expedience and efficiency. So the winner would be the quadratic according to the math behind it. And you could see that the quadratic seems to fit a little bit better than the linear did. All right, but it's not going to fit any better, or the cubic is not going to fit any better than the quadratic. If I click on that, you see it looks exactly the same. If I zoom out, you see that they look different for larger values, and smaller values. They kind of get a little crazy. They look different from one another, but in the relevant interval, they look exactly the same, right? So that's all we care about is the relevant interval, right? So I know that was a lot, and I know I kept you a little bit late, but it was definitely for a purpose. So let me stop the recording before I forget.